Well, good evening, ladies and gentlemen. My name is Paul Davies. I'm director of the Beyond Centre for Fundamental Concepts in Science. And a few words about what the Beyond Centre is. We are a research unit that tackles the deep questions of existence, things like the origin of the universe, the origin of life. And Amanda assured me this would stop. And whether time goes round and round and round in an endless loop. And it's going to start again. That'll fix it. Where was I? Yes. And so one of the things that we like to think about is the destiny of mankind and whether we're stuck on Earth or we're going to spread out into the universe, and if so, how are we going to get there? And one of the annual lectures that we do, the Eugene Shoemaker Memorial Lecture, examines matters of space. I'm going to hand over shortly to Kip Hodges, the director of School of Earth and Space Exploration, to say a few words about Eugene Shoemaker. Let me at least put his picture up. Anyway, more of that in a moment. So for those who are interested and got here a little bit earlier, you'll have seen our little flyer for tomorrow, where we have a whole day symposium dedicated to exploring the future of humans in space. And so tonight is a curtain raiser for that more extended event, at which you can also hear the science fiction writer Kim Stanley Robinson, the Mars exploration advocate and aerospace engineer Robert Zubrin, who's with us here tonight, the CEO and president of Virgin Galactic, George Whitesides, and various ASU faculty. And this is being jointly hosted by the School of Earth and Space Exploration and the Center for Science and the Imagination. I've heard a rumor that the person sitting in the winning seat will have a free ticket on Spaceship Two, but I don't guarantee that. If you're interested in coming along tomorrow, see any of the organizers here this evening and we will enroll you. So now, before I introduce the speaker for tonight, Dr. Andrew Thomas, I'm going to call upon Kip Hodges to come forward and just say a few words about this much-loved scientist, Eugene Shoemaker.
Thanks, Paul. Every year about this time, the Beyond Center has this memorial lecture for Gene Shoemaker, and it's a great opportunity for us to recognize someone who's made a major contribution to space exploration, but also it's an opportunity for us to remember Gene Shoemaker himself. Gene was a wonderful man and an extraordinary scientist. He started his career as an earth scientist. He was an undergraduate at Caltech, actually did a master's at Caltech. Finished his master's by the age of 20. He was principally working on metamorphic petrology at that time, which means that he studied the mineralogical and chemical changes of rocks deep within the Earth's crust. Had no real interest, permanent scientific interest anyway, in planetary science at that point. In fact, there wasn't even really such a thing as planetary science much when he was going through college and at that point. And after he got his degree, his master's degree, he went to work for the U.S. Geological Survey, where he was looking at uranium distribution in rocks in the western U.S. He was mapping volcanic landscapes. And he got more and more interested in things that looked a little bit like volcanoes, but actually were, as it turned out, meteor craters on Earth. So he got more and more interested in one particular meteor crater, the one in northern Arizona that we call Meteor Crater now, and eventually did his PhD work at Princeton on Meteor Crater, all the while being an employee of the U.S. Geological Survey and being interrupted to go out and make field maps every once in a while. And when he finished his PhD work, he got more and more interested in the notion of actually taking field geology, terrestrial field geology, to other planetary surfaces, in particular to places like the moon. And so he started advocating doing things like making geologic maps of the moon, which at that time was a really unheard of thing. And in many ways, Gene was one of the principal architects of what we now think of as planetary science. He was enamored with the space program. He was enamored with Apollo. He was very enthusiastic about potentially being an Apollo astronaut. In 1963, he was diagnosed with a medical condition that precluded him from being an astronaut. Otherwise, he probably would have been the first scientist to go to the moon at that time. He was the founding director of the Center for Astrogeology of the USGS that's up in Flagstaff, as you know, and still is up in Flagstaff at this time. And he was instrumental in the training of many of the Apollo astronauts who eventually did go to the moon at that point. After that, he became progressively more interested in the discovery and the development of surveys of asteroids and comets. He and his wife, Carolyn, made an incredible number of discoveries of asteroids and comets, and you may be familiar with one of the more famous ones that was named after him, and Levy, the Shoemaker Levy 9, which he managed to see before his death just a few years ago. He managed to see actually collide with Jupiter in a very spectacular way. So we're very proud of the fact that this memorial lecture occurs here every year in the School of Earth and Space Exploration, because Gene was in many ways the personification of this kind of transdisciplinary scientist that we like to celebrate. Gene was an Earth scientist. He was also a planetary scientist. He was also an astronomer. And he really walked across all of those different capacities. So thank you, Paul, for having this every year. And thank you, Andy. We're looking forward to the talk tonight.
Thank you, Kit. Well, now to tonight's speaker. When I was growing up in London many decades ago, we had our chemistry master was given the invidious job of being careers master. And he was pretty hopeless. People would go along and say, well, how do I become an electrical engineer or a carpenter or a civil servant? And he'd give them some leaflets. So somewhat out of mischief, one day I said, I want to be an astronaut. And he looked at me in total consternation. And it was clear that he wasn't going to help very much. And so I said, well, okay, how about an astronomer? And he still was very unhappy. And he said, I remember his comment well. He said, well, it might be possible, but I don't suppose there's much money in it. Anyway, I'm sure that something like that must have happened in the past of tonight's speaker, because he is a real live astronaut. And he probably, like many young people, set out with that dream, but it's not many of us who can claim that that dream came true. So Dr. Andrew Thomas comes from South Australia. He was educated, grew up and educated at the University of Adelaide, where I myself worked for some years. Has a PhD in mechanical engineering from the University of Adelaide. And I thought, in view of the Australian connection, I would come wearing not just an Australian tie, but a tie from Adelaide, no less. This is from the Tandanya Aboriginal Cultural Centre in Adelaide. So that explains the tie. Anyway, Andy worked in the aerospace industry and at JPL briefly before he joined the Astronaut Corps in 1992, and he's flown more than 70 million miles in space. So any physicists among you can think about what does that statement actually mean. Not very much, actually, in terms of how far has the Earth moved in that time. But no, it sounds very impressive, but I guess you don't collect frequent flyer points when you're in orbit. But his missions include some amazing things, like 141 days on the Russian space station Mir, the hardest part of which I imagine was learning Russian in order to be able to order dinner, but perhaps you'll tell us about that, and a 6.5-hour spacewalk to fix a problem on the International Space Station. Now, again, when I was a student, the moon landing was in everybody's thoughts. Everyone thought that the landing on the moon was the first step on a stairway to the stars, and that human destiny definitely lay beyond Earth, well captured by the movie 2001, A Space Odyssey, where you saw the clips a little bit earlier. All this looked achievable back in the 60s and 70s. 4 decades later, however, humans remain stuck in low Earth orbit. So what happened? Why are we not boldly going? Well, here to tell us why not and how we can fix it is the 2012 Eugene Shoemaker Memorial Lecturer, Dr. Andrew Thomas. Andy.
Thank you very much, Paul. Thank you, Paul, for that fine introduction. It is a splendid tie. Mine comes from J.C. Penney's. The title of my talk is Why Aren't We Boldly Going? And as Professor Davies alluded to, it's about human spaceflight, where it is now, how it got to be where it is. And I have this subtitle to the talk, which you can see here. What can we do about it? Because that's really the important part. What can we do about it, given all the constraints that we have? To understand where we are today, I think it's necessary to look at past history of how we got to the point that we are today. So for many of you, you may remember the Apollo landings. For some of you, you've only seen it on TV. But just imagine that you are standing on the surface of the moon one summer morning in July 1969, and you looked up, you would see this. This is obviously a digital reproduction, but it uses actual vehicle rates and the communication loops to depict the event. And it gives you a better idea, I think, of what an extraordinary accomplishment this really was. You would see initially a small point of light coming up over the horizon, bright blue probably, coming towards you. It would grow in size and then start to descend, as you see here. And as you come in, you start to see the dust being blown up by the descent engine, thrusters firing to maintain stability. Just remember, this had never been done before. All right, I can hear it. We're having sound problems, I apologize. By any account, this was a remarkable accomplishment. This took place in 1969. That is 66 years after the first human-powered flight at Kitty Hawk, after the Wright brothers. In that time, they went from flying a small fabric-covered biplane, less than 100 feet, to flying and landing on the surface of the moon. In the course of one human lifetime, what an incredible accomplishment that was. Certainly, we haven't seen anything of that magnitude in the intervening years. How was that possible that that was achieved? Well, you need to understand all the things that were happening in the US at that time to understand how all the forces came together in this perfect storm of events that led to the success of Apollo. If you were an engineer that worked on Apollo in the 60s, you were probably raised in the 40s and the 50s. You were almost certainly white. You were almost certainly male. And when you grew up, you read some exciting magazines like Collier's magazines. You read science fiction works like by Asimov and Heinlein and all the others. And this really captured in you a sense of adventure. And on Sunday nights, you probably watched Disney World, and you probably saw this iconic German scientist. All scientists of the time had to have a German accent, and he did, as von Braun. And he was very skilled at communicating in a way that appealed to the public the value of human space exploration. So the culture in the 50s was set for the development of spaceflight. And everyone thought that with all the advances in aviation that were taking place, things would just slowly progress. We would fly higher and faster, higher and higher, and eventually be in space. But then something happened in 1957. We had a Sputnik moment. And the Sputnik moment was Sputnik. And this was the first Sputnik moment, when the Russians flew the first orbiting satellite. This really got people rattled. And the evil empire had done something that free society had not been able to do, or so it was seen. And at that point, there were large national commitments made to education. Investments and scholarships were given to encourage studying mathematics and science. And that actually changed the culture of the United States for a generation, that event. It ascribed value to learning science and mathematics. I think the world today would be quite well off if we still had that value in our culture. But I think we've lost it. The second Sputnik moment came in 1961, when the Russians launched Gagarin, and he was the first human to orbit the Earth. And this really took people by surprise. And there was great fear in the country of a red menace, great fear of being technologically left behind. Of course, if you could orbit a spacecraft around the Earth with a man in it, you could orbit weapons. And so this really geared the country into action. A space program was forming around this time, and it hadn't flown. But as you can imagine, it got everyone excited. Once again, you see von Braun showing up in the picture as a key player in the events of that time. This led to the Mercury program and the first flights of Mercury capsule, the first 2 suborbital flights, followed by a couple of orbital flights. And even after that modest, very modest investment space flight and very modest time in flight, President Kennedy made a national commitment. Did it first in Congress and then later at a famous address that he gave at Rice University 50 years ago, last month, I think, where he committed the country to go to the moon. This was a very bold undertaking indeed, and most of the engineers who were involved in human spaceflight at the time were left stunned by it. So much so that they tried to understand what the commitment to fly before the end of the decade actually meant. Did that mean before the end of 1969, or could they fly in 1970 and still say that they were in the end of the decade? They were that worried about meeting the schedule. But meet the schedule they did. And 7 years, just 7 years after that historic speech, that defining speech, a crew landed on the moon. 5 subsequent crews through 1972 walked on the surface of the moon. To do that in 7 years was an incredible undertaking, an incredible investment of time and resources. How did that happen? How was it sustained over all of that period? In the 1960s, there were huge social upheavals. There was the Vietnam War. Yet despite all of that, funding for Apollo continued. In 1967, there was a major fire which took the lives of 3 astronauts and required a complete redesign of the Apollo command module. Yet 2.5 years later, they landed on the moon. Funding was maintained through all of that. How was that possible? There were a number of reasons that you could point to for that, but I think there is one very important reason which historians of the space program overlook. And that was another event that took place in the 60s, and that was this. That was the event, the tragic event in Dallas. This was very important in the national psyche, but it was also very important to what happened in subsequent human spaceflights. But up to this time, Apollo had sort of been this national hobby where we were going to send astronauts up into space to metaphorically do battle with the Russians on the new high ground. But after Kennedy died, the country was in mourning, the country had guilt, and the country wanted to honor the memory of this slain president. That gave a spiritual quality to Apollo. It changed it from an engineering development to a national undertaking, this whole spiritual pride that the whole country got behind. And I think space historians do not recognize the importance of this event in the success of Apollo. And Apollo took place in the 1960s over that short period of time because the confluence of all of these events led to final landing. And we haven't seen that kind of thing happen since, nor are we likely to. There was another personality that I've mentioned that was involved in all of this, and that, of course, was von Braun. And he was an amazing visionary. He was an amazing engineer, and without him, I doubt that Apollo would have happened as well. It was one of his visions. And he had a number of visions. In addition to humans on the moon, he had a vision of an orbiting space station. He had a vision of this incredibly huge orbiting space plane that would fly up and retrieve satellites and launch satellites. And he had visions of humans going to Mars. What happened to those other visions? He gave us Apollo, but what happened to those other visions? Well, we got some of them. We got the reusable space plane. That was the shuttle. Launch sequence here. Many of you may have seen launch sequences, but in this one you can hear the crew commentary during the launch itself. I've ridden on this vehicle 4 times, and I have to tell you, it is the ride of your life.
Auto. Go by the tower.
As you leave the ground, you get this incredible kick in the pants. You see the tower rush by the window, clouds rush by the window. You're burning fuel at this point at a rate of 12 tons a second. After 2 minutes into the flight, the solid rocket boosters, of course, are depleted of all their fuel, and they're jettisoned. And if you were unfortunate enough to be strapped to the outside of the vehicle, you'd see some of the views that are captured here. That's solid rocket separation, and there go the solid rockets themselves. Regardless of how you feel about spaceflight, you cannot help but be impressed by the space shuttle itself and what it can do. And it's taught us a lot. It's taught us about reusable spacecraft, how to build a reusable spacecraft. It's taught us about transatmospheric flight out of the atmosphere and back into the atmosphere. It's taught us what you need to be able to do that successfully, but it's come at a considerable price. We've learned that it's actually very hard to do. It's come at a human cost and a capital cost. When the shuttle program first started, shuttle launches were typically the order of $100 million each, 100 million with an M. After the Challenger accident, improvements were put onto the shuttle, safety features, and typical launch costs were of the order of $300 to $400 million. After the Columbia accident, with additional safety measures put in place, launch costs, depending how you account for it, were approaching $1 billion each. That is clearly unaffordable and unsustainable. And we cannot, as an agency, expect the taxpayers to pay that kind of money to have access to low Earth orbit. That's why the Space Shuttle program was closed. But that was a von Braun legacy. There was another von Braun legacy, which is the space station. He envisaged a rotating wheel space station. We didn't do that because there's actually engineering reasons why you wouldn't do that. We have a different one, which is shown here in its early stages of construction, and with a bit of digital sleight of hand, as the view pans around, you'll see the different elements, and it will morph into the final vehicle that we actually have flying today. It consists of international contributions. There's Russian segment contributions, there's some European contributions, and some Japanese contributions, and some Canadian contributions. It's approximately wingtip to wingtip, about 100 meters, and weighs about 400 tons. And currently has a crew of 6 people serving on it 24/7 around the clock. It is an incredible accomplishment. It's an incredible piece of engineering. It's an incredible piece of international collaboration to have been able to assemble this vehicle in space. You couldn't take pieces on the ground and test them together, reintegrate them on the ground. It all had to come together in space. But it's been a very costly undertaking, I have to say, and as a taxpayer, I'm a little embarrassed by the cost. It's conservatively estimated, depending how you bookkeep it, at about $100 billion taxpayer investment over, well, actually, since it was first put in place in the late 80s. That's a lot of money to ask taxpayers to pay. We have to have very sound justifications for that kind of money. I'm embarrassed that it's actually easier to use scientific notation to express the price of this vehicle. It's $10 to the $11. That's a lot of money. So where do we stand now? What do we have? We don't have the other legacies that von Braun envisaged. We don't have the Mars trip that he thought about. This is one version of his Mars Armada that he's dreamed up. I think as you read this, how he was going to do this, these 3,000-ton vehicles and nearly 1,000 launches over in 8 months, it clearly is not a very realistic prospect. And he had actually other plans for getting to Mars that were more realistic than this, and they used electric propulsion, which I think is viable for going to Mars as well. But we do not have humans on Mars. At that time, they also envisaged, that was Mars in the 80s, they also envisaged going to the moon, and in the 70s, we would have lunar bases on the moon. We were on the moon in the early 70s, but we don't have lunar bases, unfortunately. What do we have? We have the space station. That is really the essence of the NASA human spaceflight program right now. This is a view taken last year of one of the last shuttle flights. Of course, we don't have the shuttle. The shuttle has been retired. The various shuttles have been sent to their museums. This is Discovery being taken to the Smithsonian Air and Space Museum in Washington. This was back in April. I'm sure you probably know Endeavour was shipped to California just a few weeks ago. In fact, I think it did a pass over this city. Those flights have shown that there's a lot of enthusiasm and support for the shuttle program. It's near and dear to many people. It's kind of ironic, I think, that these flights earned more interest for human spaceflight than the actual flights into space, I'm sorry to say. But what about these other destinations? What are we doing there? We do not have a human presence in these other destinations. But we have very significant investments in robotic exploration of these destinations, and I'll say a little bit about that. Consider, for example, the moon. This is from a Japanese orbiting probe showing Earthrise over the moon. We've learned a great deal about the moon. The surface of the moon represents a landmass area about the size of Africa. And we've been with humans to 6 places, and that doesn't tell you a lot. We've learned a lot more about the moon than we knew from Apollo from these orbiting assets. We've learned, for example, that there's water on the moon. In fact, if you look at some of these craters, it turns out because of the way the moon rotates in its orbit, some of these craters are permanently dark. They've accumulated over millions of years, cometary material, ice, deep down in the craters where it's extremely cold, there's cold traps, and that ice is still there. That is an amazing discovery to think there would be ice on the moon. As a result, we've been mapping the moon in unprecedented detail with orbiting satellites, and much of that work stems from this university. And this is an interesting picture. This is actually the Apollo 11 landing site. This is an exploded view down here on the right, showing the descent stage of the Apollo 11 lander, still there. And you can see the footprints from Neil and Buzz that are still there, and I'm told they will remain there for billions of years. I'd like to think that the conspiracy theorists will no longer say that the Apollo landings were faked, but fortunately they just say this is Photoshop. One part of lunar exploration that got eclipsed by Apollo and that was not talked about very much was the Russian robotic probes that went there in the 60s and 70s. And they sent rovers to the surface of the moon, and they did sample return from the surface of the moon. This is really quite significant because they learned a lot by doing that. In fact, the Lunokhod 2 rover still has the world record for distance traveled on a planetary surface. It hasn't been eclipsed by any Mars rovers. They got sample return. They got material back from the moon. They didn't get nearly as much as sending humans got, but they got that at a much lower cost. And of course, Apollo was not about samples of lunar material. It was about sending people to the moon. But this did demonstrate that robotic probes can do an awful lot of scientific inquiry on these planetary bodies. The fact that there's water on the moon is actually an amazing discovery, and I hope everyone understands I've exaggerated slightly the depiction of water. But it's a game changer for human exploration of the moon because it means that you can use water as a resource. Humans need water. You can use it for drinking, but you can actually do a lot more with it. You can electrolyze water and make oxygen and hydrogen. Oxygen you can use for breathing. Hydrogen you can use as propellant. You can also use oxygen as propellant. So you don't have to carry those resources with you from Earth, out of the deep gravity well of Earth with all the costs that are associated with doing that. So you would think that that would make going to the moon a national imperative, but it's not. In fact, by law right now, our next destination is one of these. It's an asteroid, and these are some sample asteroids. These are actually main belt asteroids, except Eros, I think, is a near-Earth object. And we've learned a lot about these in recent times. We've learned one thing is that there's an awful lot of them out there, and that there's more and more being discovered all the time. They come in a range of sizes and a range of compositions, and they're actually very interesting objects in their own right, because these objects represent accumulated material from the very earliest formation of the solar system. So in that sense, they're a time capsule of the formation of the solar system. So they're worthy of study in their own right. And it has been proposed that we would have human missions to one of these. If you're going to send to humans one of these, you've got to pick the right one. Now, you wouldn't send them to one of these so-called nickel-iron asteroids. That's a very expensive way to get a sample, and the easier way is just go to the nearest natural history museum and get a piece. But there are some that have interesting materials in them. There's some that we think have organic materials. They have amino acids in them. They are perhaps some of the materials that seeded this planet, the subsequent origin of life. So there's unquestionably good reason to study them. I do question, however, whether you would want to send humans to one of these. It turns out sending humans to one of these is actually quite difficult. It takes probably upwards of a year to get to it. You have a couple of weeks there, and upwards of a year perhaps to come back, depending on which one you go to. That is a very difficult undertaking. That is not a trivial mission to do that, just to have a few days at an asteroid. For the same cost, you could send a multiplicity of robotic probes to go and sample a number of these things and bring samples back. Or you could send one probe that would go from one to another, and you could do that far more cheaply and far more safely, sending humans. So I'm actually a believer that if you're going to study asteroids, the best way is to do it with robotic probes. So there's the moon, there's asteroids. There is, of course, the gold standard of exploration that we all talk about, and that's Mars. And everyone talks about going to Mars as if a human mission to Mars is on the horizon. And indeed it is. But you must remember what the definition of a horizon is. Mars exploration by humans is a bit like fusion energy. It's 30 years away. It's been 30 years away for the last 50 years. And it still is. And unfortunately, we are not closer to sending humans to Mars now than we were back in the 60s and 70s. Why would you want to send humans to Mars? Well, there's a lot of interesting reasons, but I think some of the robotic probes that have gone to Mars in the intervening years have told us an awful lot that we didn't know. We now know that Mars is once a much warmer and wetter place than it is today, and that we know that today, even today though, it still has a hydrological cycle of sorts. And this is a series of photographs of a crater wall taken at different times during the Martian season. And you can see these striations coming out. I've turned the photo upside down so that it flowing downhill is down. And this is evidence of water flowing on Mars. Now, the physics of how this actually flows is certainly not well understood by me, because atmospheric pressure is extremely low, the temperature is very low. In fact, it's because the temperature is low that it does this. But clearly, there is some active hydrological activity on the surface of Mars. And sometimes it comes to the surface with spectacular results. And these are from orbiting assets, but you also know, I'm sure, that we have rovers on the surface of Mars, and you've all heard of Spirit and Opportunity and the amazing discoveries that they've made, the great photographs they've sent back. And most recently, I'm sure you've heard of this landing by Curiosity, this really gutsy landing that the JPL guys came up with, where they lower this car-sized lab down to the surface of Mars from this propulsion unit and then cut the lines, and the propulsion unit flies away. And it worked. And there was no one more surprised than I that it worked. But it was a great undertaking, and I'm sure we're going to get some spectacular results out of this lab. And I suspect that it will ultimately have the record for distance traveled on a planetary surface as it undergoes its mission. So, with all of these great interest in these planetary bodies of one kind or another, and all of these discoveries, and the fact that we now know there's water in many of these that make it fit for human habitation, why don't we just set a destination and go? Why don't we do another Apollo? Well, various presidents have tried to do that, and they've all tried to have their Kennedy-like moment. George Bush tried it in, I think, 1989, and nothing came of it. George Bush Jr. tried it with his vision of space exploration and constellation. That got cancelled. Even the current President Obama tried it, has put us on this course towards an asteroid, but that's not going to happen in his presidential tenure, even if he's re-elected. And chances of it actually going through to completion, I think, are very remote. In fact, the agency doesn't have a very good track record of maintaining successful programs, seeing programs through to completion. Even Apollo was cancelled once success was achieved, and it was cancelled quite quickly. You shouldn't forget that the public interest in human spaceflight does wane very quickly. The shuttle, although it was originally approved for defense reasons, was cancelled after it became unsustainable, with DoD pulling out, and then after the Columbia accident. Space Exploration Initiative, that was the initiative that George Bush Sr. tried to start, but that never got beyond the PowerPoint stage. Or I shouldn't say PowerPoint. They didn't have PowerPoint then. It was ViewGraph stage. But it was canceled. And the space station, which we have today, the only reason we have the space station today is because of the Russian collaboration. It became an instrument of national foreign policy. In fact, the space program that run by the US government has always and always will be an instrument of foreign policy. We shouldn't forget that. Had it not been for that, it almost certainly would have been canceled because it was passed in Congress by just one vote. And VSE is the Vision for Space Exploration. That was from George Bush Jr., and that was canceled after the Obama administration came in because it was politically, economically unsustainable. So we have this track record of canceling programs and not seeing them through to completion. So why does that happen in the face of the NASA budget? A lot of people say, well, it's the Democrats. And a lot of people say, well, it's the Republicans. Whose fault is it? Well, my background is as an experimentalist, and I like to look for data that would substantiate one view or the other. And this is the NASA budget over the last 22 years. And this looks like quite a healthy budget, actually. You would look at this and say, well, it's been steadily increasing over many administrations. Why can't NASA do these things, this kind of money? But this is not a very fair measure of what NASA's resources actually are. You've got to correct this for inflation. That's the buying power. This is the inflation-corrected NASA budget, and you can see a very steady trend downwards. In fact, it's a trend that's going to become even steeper as we face the fiscal realities this nation is facing. A better way to look at it is here. This is NASA's budget as a percent of the federal budget. Now, a lot of people think, well, NASA's budget, of course, is 20-something% of the federal budget. It's not. DOD is. NASA's budget is not. Right now, it is less than 1/2% of the federal budget. It's equivalent for you to buy about a pack of chewing gum every week. Everyone in America buy a pack of chewing gum a week is NASA's budget. When there were the big bailouts of Wall Street in 2008, and those billions of dollars were sent to Wall Street, Christmas bonuses were given out. Now, why that was done, I don't know, but the Christmas bonuses given out on Wall Street using government funds greater than NASA's annual budget. I'll let you decide which would be the better investment. At the height of Apollo, this budget in 1966 was 4.5%, thereabouts, federal budget. We're down less than 1/10 of that today. Now, as I said, I'm an experimentalist. When I look at data like this, what do I like to do? I fit a curve to it. And there you see it's described quite well by a straight line. And then the next thing you do is, if you've got a straight line, you extrapolate. And so in 2029, we will turn the lights out. And for those of you who are mathematicians, you know there's two ways that something can become zero. The numerator can go to zero, which means the NASA budget goes to zero, or the denominator become extremely large. So now don't think, if that means the federal budget would be extremely large, don't think that means wealth is around the corner for us. That means what it really means is hyperinflation. Unfortunately, I think both of those are real possibilities. We should be concerned about them. So here we are. This is where the agency is right now. It's really at risk of becoming just a jobs program supported by congressional districts in certain key areas. Community is very divided regarding space exploration. Some say just pick a destination and go, but I think we know that that doesn't work. It's been tried, and it doesn't work. For others, a lot of people say it's just an appalling waste of money. It's money being thrown away. It's not, of course. It's a significant investment, and it does give a return on investment, but they just see it as a waste of money, that there's other investments that you should be making. And sometimes I have a lot of trouble. I have a lot of trouble with 10 to the 11th dollars for a space station. For some, it even poses a threat to belief systems, and I'm going to just say a little bit about that because I go on the road giving public talks about exploration, and I promote the idea of humans going to Mars, and people say, well, why do you want to do that? I say, well, look, we might find evidence of life there. And just imagine if we found life had evolved once on Mars, independently of life on Earth. Just think through the implications of that, of how significant it would be, and what that would mean to us as a community, species, what it would do to our religion. About this time, people sort of look down and they get rather serious and they say, oh, I don't like that. They're not comfortable with that. There are people that are not comfortable with answering those really profound questions. I think they're fascinating questions, but rather than answer those questions, some people prefer just not to ask the question. And I think that's actually a very troubling trend in our community. A few weeks ago, a congressman who serves on the NASA Science Committee, now that's the committee that signs the checks for NASA, he came out publicly and said, with some pride, that the Big Bang Theory and evolution were just to distract us, and the Earth was actually 9,000 years old. I don't know how he came up with 9,000. I thought the accepted age was 6,000, but what's a few thousand years? That's actually very serious, I think, because this is a person supposedly with a scientific background serving on a committee that adjudicates science in the United States. I think we as taxpayers should be very concerned about it. I personally feel that people like that have an intellectual impairment to science. They're intellectually handicapped. They should not be serving on a science committee. I think there is a very serious debate that this nation should initiate at some point as to whether people with values like that should be representing people, country in Congress. I have my own views on that, and you can imagine tone what they are. But it's very serious. The result is that we have this view in this country that's rather like what's depicted in this cartoon. There's sort of sometimes ambivalence, sometimes interest in the space program, but people say, well, why? What is the reason for doing it? And I've thought about this some, and I've tried to come up with why do countries do big programs like space program? What is the value added for the community of doing one of these adventures like Apollo? Former NASA administrator Mike Griffin likened it to building the Gothic cathedrals in medieval Europe. He said, great countries do great things and leave great legacies. That argument had some truth, but it never resonated with the public. It never gained any traction. And I think there's a reason why, is that it failed to really address the reason why countries, nations do these big undertakings. And I think there's three of them. And they're shown here: economic interest, national security, and spiritual interest. In the economic interest, things like Columbus and sailing west, that was driven by an economic imperative. It wasn't to prove the world was round or for exploration. It was to open up a trade route. Interstate highway system was an economic imperative. Tennessee Valley Authority was an economic imperative in this country. Another reason we do things is national security and defense. Great Wall of China is a huge human undertaking. It was done for defense. Manhattan Project, likewise done for defense. The interstate highway system was also done for defense. It was to get goods and equipment across the country. Importantly, in the spaceflight business, Apollo, shuttle, and the space station were all born out of a defense posture. And it was defense that was used to justify them. The space station originally was justified to Reagan on a basis of national defense. The space shuttle was justified to Nixon on a basis of national defense. The idea was that the shuttle would go up and grab Russian satellites and bring them back to us. It's a crazy idea, because the Russians would just blow up the satellite, and that would be embarrassing. They do it when it's in the shuttle. There is another reason why these large human undertakings sometimes succeed, and this is the spiritual side of them. And that's why pyramids were built, because it appealed to a spiritual deity. Gothic cathedrals were built as a result of that. Crusades done for that reason. And importantly, Apollo was done for that reason. The reason I said, because it was a way of honoring the memory of John Kennedy. And there's a reality that we have to accept, that if we want to do human spaceflight as a large funded government program, which has been the paradigm to now, it needs to appeal to one of these imperatives. And if it doesn't, it's not going to get funded. And that's the history we've seen. I call these wealth, war, and worship. It's also called gold, glory, and God. And these are the imperatives that you have to have if you're going to have a large government-funded space program. Others say, don't worry, let's just have another Sputnik moment. And there's one coming. People say, don't worry, the Chinese are going to tramp all over our flag when they go to the moon in the next decade. I don't know if that's going to happen or not. I think the Chinese do have plans to go to the moon. I don't know if they would do this. This is really meant to be a metaphor for what's going to happen, not necessarily literal. I don't think they would do it literally. Although I've heard that some Chinese officials would like to bring one of the Apollo flags back and present it to this government. Would you like to be the political leader receiving a flag from China? I just imagine the symbolism that would go with that. Don't look for re-election anytime soon. So this won't literally happen, but metaphorically it probably will. And it would be a Sputnik moment, but it won't be enough, I think, to galvanize the nation into action. I think it'll generate a lot of sort of text in the blogosphere, but it won't be enough to galvanize the nation. Because the nation does not have all the elements that preceded Apollo working for it today. So here's the challenge for human spaceflight. This comes to the second part of my talk. I've talked now about what we've done. What are we going to do about this? How are we going to fix this problem? And I think we should have no expectation that Congress will ever fund a long-term plan beyond many election cycles for funding a large-scale Apollo-like program. It's simply not going to happen. So what is the path forward? How can we get NASA out of low Earth orbit? NASA has been in low Earth orbit for the last 50 years. We know how to do that. Been there, done that, got the T-shirt. We've got to move on. And I would like to propose a path forward where we can do that. And I should say, in the interests of full disclosure, this is not an agency position. This is not NASA talking. This is me talking. This is my personal belief about what we should do. And I think what we need to do is take a series of small steps. Because to paraphrase Neil Armstrong, giant leap is not possible for the reasons I've described. A series of small steps are possible. And enough small steps, if done consistently, according to a plan, can accumulate to a giant leap. First thing we need is creative ways and innovative ways of achieving space exploration beyond low Earth orbit. Small steps is a way of doing that. I think we need a much bigger synergism between humans and robotics. I've shown you some of the great discoveries that robotic exploration makes. And there's this ongoing debate. Should you send humans or should you send robots? The answer is you send humans where humans do best, and you send robots where robots do best. But do them together. I think we need to do that. I think NASA also needs to reinvent the way it does engineering. It needs innovative approaches for engineering development. I'll talk about that. I think Congress must unfetter NASA from some of the legal restrictions about partnerships with other nations. I think this nation must accept risk. If we're going to do human spaceflight, it's a dangerous business, and you just have to accept risk. Realistic risk, though. Most importantly, Congress and administrations must not change the NASA directions every time there's an election or a new administration. That's happened almost every 4 years. We need stability, not just in funding, but in planning. We need to be able to put plans in place that have an outcome that's beyond the next election cycle and have an expectation that we'll see it through to completion. So let me say a little bit about each one of those. Firstly, about the small steps idea. At the top of the screen here, you see some of the elements you need if you want to do exploration beyond low Earth orbit, what I call deep space exploration. Regardless of where you're going to send humans, you're going to need certain things. You're going to need propulsion stages, chemical propulsion stages, probably cryogenic chemical propulsion stages, electric propulsion stages, possibly nuclear propulsion stages. You're going to need habitats. You're going to need a habitation system that will keep a crew alive for months at a time without resupply from the Earth. We don't know how to do that yet. We haven't been able to do it. And if you're going to land on surfaces like the Moon or Mars, you need landers. Regardless of where you go, you need these kinds of elements. Right now, the idea of setting up a program and developing all of these at one time is unthinkable. It's just not going to happen. It's unaffordable. It's not realistic. But we can do small pieces at a time and slowly advance to the capability that will get us beyond Earth orbit. I would propose beginning by starting with a small, modest mission beyond low Earth orbit. And if you're going to do that safely, the place to go is near Moon space. I would use existing elements to do that from the space station. You might actually take elements from the space station itself, although that turns out not to be very efficient. But we've got enough test articles and enough hardware on the ground that we could repurpose them for use as deep space modules. We could put together a small, very small, modest deep space habitation system and propulsion system and send it into lunar space. It could go into orbit around the moon, or it could go to one of these what are called Lagrange points, where the gravity and centrifugal forces balance out. You wouldn't have humans in it around the clock, but you'd have humans visit it. I think that would be a very good way of getting us out of low Earth orbit. Now, what are you going to do there? We'll say, well, if you're going to go to the moon, build a lander, and you can land on the surface of the moon. I don't think we should do that. I don't think we should send people down to the surface of the moon until you have an imperative of sending humans onto the surface of the moon. And sending humans to go down and gather a few rocks in $1 billion lander just doesn't make sense. You could send a robot to do the same, much more cheap. Russians did it in the 60s, 70s, rather. And that was one of the problems with the Constellation program. This is the lander that the Constellation program was going to build. This lander is huge. Weighs, when fueled, over 50 tons. I was going to say it's the size of a small house, but that's not true. It's the size of a large house. It is a monster. Each one of these landers probably would have cost, conservatively, probably $2 billion. Each lander. Each lander was going to be used one time and then thrown away. That is unsustainable exploration. Cannot expect taxpayers to foot the bill, those kinds of dollars, these kinds of vehicles. We don't have the funds to do it. So what are we going to do if we have a human presence in near lunar space? Well, there's a lot that we can do. We can do it robotically, as I said. There is a prize that many of you may know called Google X Prize, Lunar X Prize. Google is offering a cash prize to someone who can land a small rover on the moon, drive. And there's a lot of entries that are going to do that in the coming years. So there will be a host of landers developed as part of that process. NASA will be able to buy a lander, small robotic lander, off the shelf. We could take one of those landers and we could deploy it onto the surface of the moon and conduct exploration remotely from this human-tended presence orbiting above the moon. We could be orbiting above the far side of the moon, looking at sites that have never seen before. We could deploy excavators and resource extraction systems to test the idea of extracting resources on the surface. Finally, we could actually do a sample return. One of the prime geological interests, top 10 decadal science interests for lunar exploration, is to return a sample from a deep impact basin, South Pole Acre Basin, far side. We could do that using one of these small landers, put with a small ascent vehicle, and send it not back to Earth, but up to the crew who are in orbit. That actually has huge mission advantages for this vehicle because it does not need to carry an Earth entry system, a landing system, heavy parachutes. So you can make that much smaller, the whole vehicle downsizes, and it makes it much more effective if you have a way of retrieving the sample. And I'm proposing that we have human presence there to do that. I think the human presence in lunar orbit can actually support a lot of other exploration too, and it can be a stepping stone to your ultimate getting to Mars. For example, another science goal of prime interest is a Mars sample return, to bring back a sample from a known site on Mars. To carry a return vehicle with an Earth entry system and landing system and parachutes all the way out to Mars and all the way back is a huge penalty. If you can bring the Mars sample back to the lunar space, save thousands of spacecraft. It's a huge benefit. It really makes this mission much more attractive. There's another reason why you want to do it too, because there is a community that are very concerned about the idea of bringing a sample of Martian material back to Earth. They don't know that thousands of them down the Antarctic Museum. Some of these people are not very realistic. And there are planetary protection requirements in place as a result of that. By bringing a sample back to near moon space, you can protect the Earth from contamination, Martian. But you could do some of the assaying and study of the sample prior to. So having a crew in near lunar space greatly assists with this kind of planetary exploration. What about an asteroid? How do you do asteroid exploration from the moon, lunar space. Well, the JPL guys have come up with a clever idea for that. They say if you can't get to an asteroid, bring the asteroid to you. And they've come up with this mission plan where they would go out and literally bag an asteroid and bring it back to Earth. And the first time I heard this, I thought, that's nuts. But it's actually a good idea. Now, you do it with electric propulsion and low thrust, and it takes about 5 years to get back to Earth, but it doesn't matter. And you can bring it back to near lunar space, where geologists like Kip here would fly up to it and study it endlessly. And you could do that at far lower cost and far greater safety than actually sending out to the asteroid itself. So after a few years of operating in lunar space, you would have conducted a lot of planetary science investigations on the moon and asteroids and possibly Mars. You would have got a lot of flight time on the systems that you require for deep space, the propulsion systems, the electric propulsion systems, the habitation systems, the life support systems. So you would now have a craft that's viable for further deep space exploration. This is like the test flight approach. This is like if Boeing built a new aircraft, they don't just take it to the airport, fill it with people, and fly it to Tokyo. They do high-speed taxi runs. They do low-speed flight, low-altitude flight. They increase the speed. They look at stall margins. They slowly expand the envelope of operation to develop confidence. That's what I'm proposing with this. It's the same kind of approach, to develop confidence in your systems so that you can then do other things. If you decide that the national imperative is that we're going to return to the moon, or if there are commercial interests in returning to the moon, this vehicle could support lunar landings. But now you have a lander that doesn't get used one time. It's a taxi. It can go up and down and be refueled with supplies brought from Earth. So you don't throw it away every time. If the imperative is to go out into deep space, do so. In fact, if the imperative came to go to Mars, you could use this vehicle or the flight-certified components of this vehicle, the engineering of this vehicle, send a crew out to Mars. And this is one mission that's been suggested, which is sending humans to the moons of Mars. That's attractive for a number of reasons. The moons of Mars themselves are quite interesting. They probably captured asteroids. They also have Martian material on them. The crew would have a certain amount of safety and protection from the asteroid itself, and you don't have to build a lander that goes down into a deep gravity. And so you could do a lot of very useful planetary science exploration with kinds of systems that I've talked about here. And I believe that if we did missions like this into the Martian sphere, it would be inevitable that we would also start generating interest in going to Mars, and that we would have parties coming forward, plans, landers, and we would eventually end up on the surface of Mars. So this is a way of creeping on that final destination. Now, I don't propose that we do this because of timidity. I do it because of practicality. I propose this kind of, because this is the only way forward. We can't do these big, expensive programs. We've got to. Now, if we're going to do this as an agency, there's a few things we need to do. We need to do things differently at the agency. I'm sure you all recognize this. This is the project lifecycle flowchart that NASA uses. This is the main system engineering process that NASA uses for developing all its flight qualified systems. I printed this out with the smallest font that I could, and it was a chart 6 feet long. And your first reaction is, well, that's just a mindless bureaucracy gone mad. It's actually not. There's a sound reason for this. This process, this complex process, allows very complicated spacecraft to be engineered with a level of detail that's really unimaginable. This process actually derives from DoD and their acquisition process. But because you've got this, you understand the heritage of your vehicle. For example, if an integrated circuit fails, say, 10 years from now on the space station, you can go back through the paper trail that this process requires, and you can find the very date that that circuit was made, the very factory it was made, the lot number, and you can find out if there's other similar circuits on the space station. And it allows you to do that. So in that sense, it's a very impressive accomplishment. But it comes at an incredible price because it takes a cast of thousands to maintain this engineering. There's a general recognition arising at NASA that we cannot continue to engineer systems by this method. We've got to find alternative approaches out of business. NASA right now is kind of like where IBM was back in the early 80s. IBM had a complete lock on all computers. They were big blue. They had everything. They weren't threatened by anyone, so they didn't need to change. They called the shots. They didn't notice a couple of young upstart companies coming along who nearly put them out of business. Microsoft, Apple. It's amazing that IBM actually survived. I think NASA's in the same position. NASA has got to adapt to a new environment or it won't survive. That was the engineering process. This is the flight operation process for preparing a shuttle. And this is about a 2-month period. Now, this assumes to prepare a shuttle for launch, like I showed, you have all the elements. You have the solid rocket boosters, you have the tanks, and you've got to bring them together and wheel them out to the launch pad. It takes about 2 months. Now, this is admittedly engineering on a pretty big scale, but it takes about 2 months to do it. There's a lot of paperwork that has to be followed to do this. This process and the bureaucracy required was driven home to me when I was early in my career as an astronaut. I was supporting launches and landings down at the Cape, and I would have the job of going out to the shuttle on the launch pad, usually in the middle of the night, a few hours before it was about to be launched, while it was being fueled, and I had to do what was called babysit. I was in charge of the shuttle. Imagine a young astronaut. This was heady stuff, I tell you. I was in charge of the shuttle, and it was being fueled. And they would occasionally bring in payloads, called late-stow payloads that had to be installed in the shuttle. They had a short shelf life. And so I would have these crews come in, and they would bolt these payloads in place. And so I watched this happen. You had one person who had a wrench, calibrated wrench, and he was bolting the payload in place, the contractor. You had another person who was the quality control inspector for that company, who was watching the guy turning the wrench to make sure he did it right and signing off that it was done right. You had a guy in the launch control complex dictating the process of how to tighten a bolt. Apparently it has to. Because this was a government spacecraft, there was another quality engineer, a NASA quality engineer, watching the contractor quality engineer who was watching the guy tightening the bolt, and I was watching all of them. We did get the bolt tightened, though, but it demonstrated that you can't have these kinds of processes if you're going to have any hope of being competitive in developing flying spacecraft system. And there is an existence proof that it can be done more cheaply. And that's the Soyuz. I did quite a lot of Soyuz training. I got to fly on some Russian hardware, and I've been to a Soyuz launch. And it's amazing to watch a Soyuz launch, because the vehicle's in a warehouse 2 days before launch, disassembled. And then they take all these pieces, they put them all together, put it on a railroad car, take it out to the launch pad, turn the pointy end up, and it goes. And it takes 2 days. And it's done it with an amazing reliability. So it can be done. We, as an agency, need to learn how to do that. And another thing, too, we have incredible constraints on weather in our launches down at the Cape. For the shuttle, if there's a rain shower within 50 miles, you can't launch. This is the Russians in Kazakhstan. Kazakhstan in winter makes Minnesota in January look like tropical weather. I mean, it launched this day. Can you imagine? It actually launched. And look at it. We've got to learn to have systems that have much more resilience than the ones we have been flying. And one of the tragedies about the shuttle was that it was not a resilient system. It was very unforgiving conditions. I think we need to learn how to do this, or we will be like IBM. We will be put out of business. And there are young upstart companies out there trying to do it. There's SpaceX and Sierra Nevada. Even one of the big guys, Boeing, is learning how to do that. And they are coming forward and flying vehicles at costs that they claim way lower than what we've had to deal with in the past. But if NASA doesn't adapt, these guys will take over. So NASA is actually working with these guys and funding them to provide launch service. And this is what will replace the shuttle. I actually think this is one of the most positive developments in human spaceflight, because it's going to drive down costs, and it's going to give us frequent access to low Earth orbit. It's going to get NASA out of the low Earth orbit business, which we need to do because NASA needs to go beyond low Earth orbit into deep space, and this is the path forward to do it. Now, who's going to pay for it? Oh, before we go to that, by getting the focus of NASA off deep space, we can build this rocket. This is called the SLS, the Space Launch System. This is a Saturn V class rocket that is currently under development. If we can get the focus away from low Earth orbit access, we can build this vehicle. And this vehicle is designed specifically to go beyond low Earth orbit. I think this is of paramount importance to the nation. I think the nation needs this. This is the most important development going on at NASA right now, and that's what this nation needs. And I hope very much that this does not get cancelled, because if this gets cancelled, then all we have is the space station, and we won't go anywhere else. We must have this rocket. And whether you want to go to the moon or to an asteroid or to Mars, you need a vehicle of this class. But as I said, someone has got to pay for it. And people doing exploration have always been plagued with questions of funding. And you've all heard the anecdotal story about Queen Isabella, I think, selling her jewels to pay for Columbus, which is interesting because there was a huge economic imperative for him to make that mission, but everyone thought it was just unthinkable, too much risk. Couldn't do it. So the story goes that she sold her jewels to pay for the ships. Raises an interesting question. I'd like to put it to the NASA lawyers. Does that constitute government funding or private funding? I don't know. But people doing exploration have always had to solicit private funding. The exploration of the Northwest Passage was done by government funding because there was one of the three imperatives to do it: economic trade for the Northwest Passage. Exploration of the South Pole did not have one of those imperatives, and the people that did the exploration, here I show Amundsen and Shackleton, it's true for Scott too, had to solicit private funding from donors to make their missions work. That was true then, and that's true today. And I think if we're going to go and do some of these human exploration missions beyond low Earth orbit, we need to tap in to private funding. And there's people and organizations out there who wish to do it. I mentioned the Google X Prize. SpaceX, I also talked about. Elon Musk claims that he can get to Mars in 15 or 20 years. I don't know if that's a realistic goal, but if anyone could do it, it would be him. And people like James Cameron are putting money into human exploration. He and some others are collaborating on planetary resources to go and mine an asteroid. I don't know how their business case closes, but they're putting money into it. NASA needs to collaborate with these kinds of people. NASA needs the freedom to do it. That's actually very hard for NASA to do that because of federal procurement regulations, and Congress needs to unfetter us so that we can do that collaboratively with these kinds of interests. I showed previously also the case of what might happen if the Chinese land on the moon. I think this would be a much healthier event were it to happen, and that's collaboration with the Chinese, not competition. Right now, NASA is prevented by federal law from interacting with the Chinese on matters of spaceflight. I don't think that serves this country's interests. It certainly doesn't serve the interests of the wider global community. It certainly doesn't serve our strategic national security interests. And it's not good for exploration. So I hope that that policy would ultimately be changed. And finally, I'd say a few words about risk. We have become a very risk-averse nation. If we're going to do exploration beyond low Earth orbit, we need to be ready to take and accept risks. Space Shuttle, when it first flew, they thought the probability of losing a crew was about 1 in 1,000. And then Challenger happened. They said, oh, sharpen our pencils, and they went back and looked at it and said, well, it's probably more like 1 in 300. Then we lost Columbia, and we learned the real number was about 1 in 50. That is an unacceptable risk. That's why the shuttle program was closed, partly the cost and the risk. It actually turns out that it was safer to go and serve in the military in Iraq to fly on the shuttle, statistically speaking. That is an unacceptable risk, and the taxpayer shouldn't be asked to support that risk. So we need to have realistic risk paradigms, and I think we can do that. But we must be ready to accept some level of risk. Right now we're not, because Congress have stated that another accident is completely unacceptable. But there will be accidents. It's the nature of human spaceflight. So what I'm proposing is a path to get eventually to this point, and that is humans on Mars. I would like to think the first person to walk on Mars has been born. I don't know if she has yet, but perhaps she has. I certainly like to see NASA as an agency actively involved in this and as part of this. I think we need to make some changes if we're going to be. And I offer up suggestions of how this can be done. I think these sort of changes are not just something you do because it's an option. I think it's mandatory. I don't think there's any other path forward for NASA as an agency unless we adopt some of these kinds of changes. Because space is awfully big, as shown by this picture of the Earth taken from deep space, backlit by the sun. And I know what you're all thinking. He's clearly not right. That's not the Earth, that's Saturn. But actually, it is the Earth. Thank you very much.
Well, thank you so much, Andy, for that inspiring lecture. We have time for Q&A, but before we do that, I've got a pleasant duty to perform. Each year we present our speakers with this little trophy, and this will require some explanation. Would you be kind enough to take it out of the plastic wrapping? Sitting on top of this little box that has the words Andrew S.W. Thomas, and then about the Beyond Center and Eugene Shoemaker Memorial Award, 2012. And sitting on top of this box is a strange-looking piece of green stuff. That's called impactite. As Kip was explaining, Gene Shoemaker was an expert, indeed pioneered the subject of impacts. He liked anything that slammed into the Earth or the planets. And when a large meteor slams into sand, for example, like in North Africa, it fuses the sand and it makes this type of material called impactite. So what better to honor the memory of Gene Shoemaker than a piece of impactite on a box? So there we are, Andy. And now we can go into Q&A. There's no fixed time limit, but we obviously don't want to go on too long. I'll moderate this in the interests of fairness. Fairness, that is, between male and female, young and old, left and right. We have one of my assistants here hovering with a microphone. So we may or may not need that, we'll see, because the acoustics in here are not too bad. And I'm going to start with this young person right in the front here. Do you need the microphone? You might as well have it because we've got one available. And we've seen you before. So I was expecting a question from you. Go ahead.
Earlier you mentioned how a single-use space lander or rocket isn't sustainable. But isn't the Russian system for launching into space a single-use rocket?
Yes. I first got this.
Yeah, but that's probably right then.
For climbing out of a gravity well, it depends on the mission. There are some cases where it's just not practical to reuse elements of the rocket because they burn up coming back in or something like that. I think for lunar exploration, there's definite leverage and advantage if you can reuse the lander because you don't have to carry it from Earth all the way to the moon to use it. It's there. And so you save that transportation cost, you save the manufacturing cost. There's other costs. It's not a perfect solution, but I think it's superior than throwing away $1 billion every time. But you're quite right, the Russian launch vehicles are discarded, and most of our launch vehicles are discarded. You might be interested to know that the shuttle was reusable, and the solid rocket boosters were refurbished after each flight. The big tank was the part that was thrown away because it was too high to bring it back. I think I've heard that the cost of refurbishing and reusing these solid rocket boosters was marginally higher than buying new ones. That comes back to what I was saying. We've got to change the way we do business.
Okay, a second question. Lady there. It's hard for me to see with this light in my eyes, but yes, go ahead. Try it first without the mic.
Mm-hmm.
Yes, we can hear, yes.
Correct, it is, yeah. Right now, NASA is looking for astronauts who will fly missions to the International Space Station. So there's a very heavy emphasis, not so much on aviation as was required for the shuttle, but more on various sciences. I have only vaguely heard about the other activity, but I think that would be to support companies like SpaceX and Sierra Nevada and so on. And I suspect what they're looking for are test pilot skills for those kinds of vehicles that they're developing.
If you'd like to come, sorry, if you'd like to come along tomorrow to our one-day symposium, then of course we have the CEO of Virgin Galactic, and maybe that is a good way to get yourself a free ticket. Volunteer to fly the machine. Okay, now I'm going to take one from the back because then we'll come forward. Gentleman there, yes.
I actually support diverse groups. I think for too long we have focused on NASA astronauts doing it all. I think some of the developments in the commercial market are going to open up low Earth orbit access and access to the space station to non-professional astronauts. I think that would be a good thing, because if you could expand the market, you can drive down the costs and raise the interest level. I think it'll be a long time before we reach the point where we have non-astronauts going to the moon and other destinations, just because there's not a large economic or commercial imperative for other groups to send them. It'll happen eventually, but that's still a ways off.
Now, spot for choice. Young lady in the middle there.
I think it's a good idea. I mean, this is one of the things that we need to do, open up low Earth orbit to everybody. And that's only going to happen if you have a place to go. And he is investing a lot of money. I don't know if people know about this, but he's made a lot of money. I forgot how he made it. He's a gazillionaire, and he's building inflatable habitats. He's launched one. And the idea is that it's actually a hotel. And I think he's going to collaborate with companies like SpaceX to provide transportation. And there you've got everything you need. You've got transportation, a place to go, and you can open up a market. And I think that would be very healthy.
Before we take the next question, am I allowed to ask a question? Because, you know, it occurred to me as you were talking that, I mean, this has been your life and your work for many years now, but when you actually go into space, it's a terribly scary thing. Well, what is the scariest bit, or is none of it scary to you? Is it just job?
You know, you would think, you saw that launch sequence, you would think that that would be scary. And if someone told you you're going to go do that and go do it right now, it probably would scare the pants off you. But when in the profession that I've been in, we spend so much time training in simulators, which are very high fidelity, that when you get to do it, it actually has an air of familiarity. Everything looks familiar. You're in the same suit that you've worn a number of times. You're in a vehicle that looks just like all the simulators you've trained in. So it has a lot of familiarity. And you also have a lot of trust, because you know a lot of people have worked very hard to make the vehicle safe. And there's also the fatigue element. By the time you finally get to do it, you've trained so long, it's like, thank God, we're finally getting to go. You're really pleased that something interesting is going to happen at long last.
Well, thank you. Another one in the middle there, and then I'm going to go over to the right, then to the left. And yes, you there, sir.
We've learned a lot about the effects of microgravity. We've learned that if you don't do anything, microgravity can be very bad for your muscles. It can be very bad for your bones. It has the same effect as people who are bedridden for a long time have. They have deterioration and calcium loss, structural loss from bones and muscles. We've learned that you can fix that by exercising. If you have a good exercise regime, you can overcome that. There are some other effects. We have discovered recently, crews returning from the space station, some of them have suffered interocular pressure increases, which has led to permanent vision changes. This actually is quite serious because it arises from intracranial pressure increases. We don't fully understand this problem yet. We need to find ways to mitigate that, but I'm sure we can mitigate that. And I don't think a 6-month trip to Mars in zero gravity is anything to be scared of. There's a lot of people who think that, well, you need artificial gravity and you need to rotate the spacecraft. I don't think that's the right answer. I think you can do it in zero gravity, provided you have a good exercise regime.
Okay, as promised, so a question on the right. Could we have a question from a woman? Do I see one? Yes, on the end there.
Okay.
The lady on the end, could you just speak up and we'll try to hear you, and I'll repeat the question if not.
Have I sold any of this to NASA since talking about it, and are they receptive? I try to sell it. They are receptive, but there's a lot of people with a lot of ideas. I think there is a general consensus growing within the agency that some of the things I talk about have to be followed, like lean engineering development. We can't do engineering the way we've been doing it. We've got to get the costs under control, and that means you need lean engineering development. The idea of going beyond low Earth orbit is an imperative for the agency. That idea is gaining traction. So I've found the community is very receptive to it. And I'm confident that in weeks to come, particularly after the election, you'll see policy directions, I hope, along some of these lines, perhaps along other lines. But the agency does seem to be poised to go this way, because most of the management of the agency recognizes we've got to do this. If we don't do this, we have nothing. All we have is a space station, and when that's done, we're done with human spaceflight. And I don't think that's something this country should do.
There was a gentleman in the front wanting to ask one. You, sir?
Here's a practical question. My son here wants to...
Right.
It's a bit young.
We're wondering, how many astronauts are in training now? How many talks will there be?
You know, the most important advice I would give him, whatever he does, is it has to be something he loves to do. If it turns out that that's being an astronaut, then he should pursue that. If it turns out being a doctor, then he should pursue that. That's the key. Right now, there's about 50 astronauts in training for flights, and we're flying at any one time about 4. If we undertake some of these other missions that I talk about, and if some of these commercial activities like SpaceX come along, we'll be flying more and we'll increase the office. We're looking, as was mentioned earlier, to hire about 20 more astronauts right now, and we'll be about 70 or so when that happens. So when 15 years from now, it's very hard to predict, but I hope 15 years from now, we're doing some of these kinds of deep space missions that I talked about. So there will be lots of interesting flight opportunities.
And one of these 50 is your wife?
Yes, my wife is actually an astronaut. In fact, that Soyuz rocket was her launch. I had the privilege of watching her launch from Kazakhstan 2 years ago now, and it was an amazing sight, I have to tell you. to see one of these rockets launch when you know someone who's in it rather well is quite an emotional experience.
I bet it is. I'm going to take a last question from the left-hand side. And there's a hand up there, and I can't quite see. It's a young man, is it?
Are the future astronauts robots, and where's robotics going? It's going to be, I think, like I said, I think this argument, do you send robots or do you send humans, is kind of bogus, because the answer is you do both, and you do what's best. I think in some places you want robots. If we're ever going to mine water from a deep crater on the moon, we're not going to send humans down into a dark crater on the moon. It's 40 degrees Kelvin down there. They would die. You would use a robot for that, but you would have humans operating it, potentially, from the surface or from orbit. I think if we're going to examine asteroids, you'd send robots to do that and retrieve samples, because it's easier and cheaper and safer. So there's different missions that require humans, there's different missions that require robots, and there's a suite of missions where they come together, and that's what the future of human spaceflight is a synergism between robots and humans.
Now, before I draw the evening to a close, a few things. One is to repeat that tomorrow we have a whole-day symposium. It's not in this venue. It's in a different building. It's, in fact, in the building where, the new building where the School of Earth and Space Exploration is located. Anyone interested in joining us for all or part of the day should see any of my assistants who are here this evening. So that's announcement number one. Announcement number two is keep checking the Beyond Centre website for further public events. We have several per year, and they're always great fun. And last but not least, there are people to thank, because you, the audience, you show up and you get the music and the speaker, and everything works flawlessly, but it only works flawlessly because of the huge amount of work that are put in by the people who work alongside me, some of which you can see for yourself right now, like Katie, standing over there, Katie Lee. And Amanda, who was helping us set up all that, the sound and fury at the beginning. She's sitting over there in the middle. And but last and certainly not least is the woman who lies awake at night worrying about every little detail to make sure things go smoothly. That's Adriana Fontes. She's standing at the back. So thank you, Adriana. And finally, another round of applause for our wonderful speaker this evening.